Thank you. Thank you. I thank the organizers for the invitation to this nice conference in honor of Frank Loray. Thank you, Frank, and congratulations. So I will explain. We joined work with Michael Fallaluza, Arturo Fernandez Perez, and Rudy Rosas about indices of holomorphic foliations in the plane. It's not. And I begin with some facts about composition of blow-ups. So we consider a sequence of n blow-ups in the of the origin in the plane, and we denote by E1, En the ordered irreducible components given by order of appearance in the blow-up, and the intersection matrix A of the exceptional divisor. Then we introduce also the proximity matrix that it's well known for the specialist in algebraic geometry, but that I don't know its existence. We rediscovered its existence during we made the work, and it is defined as the lower triangular matrix. It is defined inductively, beginning with the stage 1 by the number 1, and then putting the previous at the left, and the minus this row vector that controls that put an 1 if in the position J, if the center of the J blow up is if the center of the K blow up is at the J component. So let us illustrate this one example. We blow up the origin, P0. We obtain an exceptional divisor E1, is a P1. And in this P1, we fix a point, P1. And then the first matrix, proximity matrix, is just the number 1. And the second proximity matrix is this one, and we put a -1 because because the point P1 is on the first component of the exceptional divisor. Then we choose a second point that, in this case, we take in the intersection of E1 and E2, and we blow up again. And then the third proximity matrix is obtained by putting the second proximity matrix here, and since P2 belongs to E1 and E2, we put -1 here and here. And this is the recursive definition of the proximity matrix. And in this case, one check that the auto-intersection, the intersection matrix of the components of the exceptional divisor, it's equal to this product of the proximity matrix transposed by itself. And in fact, this is a general fact for any composition blow-ups. And we rediscovered this saying that P gives the Cholesky decomposition of -I inverse. And we use that. If we have a curve, a germ of curve, we can consider the strict transform by the composition of the first J blow-ups, and take the pullback by the next blow-up, and we obtain the strict transform, the next strict transform, plus the algebraic multiplicity times the new irreducible component, or the new exceptional divisor. And in fact, the algebraic multiplicities at the different centers define a vector that can be computed using the proximity matrix like that, where SC is a vector that controls where the strict transform meets each component of the exceptional divisor. And this vector will appear in the sequel very often. There is a relationship between the proximity, the intersection matrix and the topology of the complement of a G-Markov curve. That is the following. We consider a reduced equation of a curve, and then the fundamental group of its complement is generated by loops gamma k along each irreducible component of the total transform of the curve with some relations. This is a consequence of the Seyfert-Van Kampen theorem, and the relations are: we have a commutation when between the loops are associated to components that meet, and for each irreducible component of the exceptional divisor, we take the product of all these loops, and so in fact we take the product of all the loops that meet associated to components that meet the component J, and it's equal to the loop along the component J to minus the auto intersection. This is the result that one can show. And passing to the abelianized, we obtain the following presentation of the homology group of the complement. That is, write these relations in additive form, and we denote C the cycles on each component, and then we can present this presentation of the homology group as saying that the loops, the cycles around the irreducible components of the exceptional divisor can be expressed in terms of the cycles around the curves itself that we have here. And from this, we obtain the vector of vanishing orders of each function along the irreducible component of the exceptional divisor is given by this product. This is a linear combination of the columns of the inverse of the intersection matrix. So let us consider an example. Is the case of the cusp E2 equal to X3, and we made a first blow up. We obtain an exceptional divisor E1, and then here we obtain a point and the strict transform of the cusp. We made a blow up of this point. Here we have the strict transform of the second stage, and finally maybe here we denote the strict transform of the global, the singularization of the cusp. And here we have C1, C2, C3 cycles around the irreducible components of the exceptional divisor, and here you have a cycle around the strict transform. And the presentation of the fundamental group in this case is given by all the things that arrive, all the loops that arrive to E1, this is just gamma E3, it's equal, the product of all the things that arrive to E1 is only E3, equal to gamma E1 2 minus the self-intersection, that is 3. The same thing for the second divisor. For the theory, we have this relation. The commutativity relations are not necessary to be made explicit because follow from these other relations. And defining capital X as the loop gamma E1 and capital Y as the loop gamma E2, we have this funny presentation of the fundamental group of the complement of the cusp. The complement of the cusp is xy e squared different from x cubed, and the fundamental group is xy e squared equal to x cubed. In this case, we have the vector SC is 0, 0, 1 because the strict transform of the cusp only meets at the component E3. And the generator of the H1 is the C, and we can express using the presentation that the cycles around E1, E2, E3 are given by 2C, 3C, and 6C. So 2, 3C, 6 are 2, 3, 3, 6 are this column, and this encodes the vanishing order of the cusp along the components of the exceptional divisor. Now, let's consider a foliation on C2, and a separatrix is an irreducible gem of analytic F-invariant curve. The foliation is dicritical if it possesses infinitely many separatrices. In the sequel, we will assume that the composition of blow-ups reduces the foliation. Okay. But the reduction in a specific in the following way. When the foliation is critical, for instance, if we have this type of foliation, critical here, that considered Laura at the first talk, then here there is no singular point of the foliation, but there is it's not normal crossings. So we continue the process of blow-ups to obtain a normal crossing divisor, like that. Here, this will be the desingularization of the reduction, or the reduction of singularities in the case of a dicritical foliation that we consider. A separatrix is called dicritical if it arrives to a non-invariant irreducible component of the exceptional divisor. It's a dicritical separatrix, and separatrix is isolated when it arrives to an invariant irreducible component of the exceptional divisor. And the next notion I recall is the germ of a balanced germ of divisor that is a linear combination of separatrices with weights -1 and 1, and 0, of course, such that if all the isolated separatrices appear with weight 1, and if a separatrix appears with weight -1, then it's dicritical. And finally, for each non-invariant, for each dicritical component D of the exceptional divisor, we have the number of weights, the sum of weights of separatrices that arrive at the dicritical component is 2 minus the balance of the dicritical component. For instance, in this case, the balance, a balanced divisor, will be C plus L, where L is a line like that, no? Because here the foliation is like that. So this is one of the leaves, and this is the only dicritical component in this case, and the sum of the separatrices, the weights of the separatrices that meet E1 is 1, is equal 2 minus the balance, that is the number of attaching points of the other components, that in this case is 1. So this is a balanced divisor for this example.
Sorry, but the coefficient of L is minus F?
Is plus in this case. Okay. Is in more general involved situations, it's necessary to put the minus, but in this case it's plus. Because with...
So in the number 2 says if...
It's an implication. If the weight is -1, is dicritical, but the converse is not necessary. We recall also the algebraic multiplicities of the foliation of the curves, the vanishing order of an equation of the foliation of the curve, and we extend the definition of this algebraic multiplicity to divisors with in the natural way, and we need to introduce two more things. So it's the definition of generalized curve, no saddle node. Saddle node is like given, for instance, x mu an equation like that. This is a saddle node, and F is called second kind. See? No tangent saddle node. Tangent means that this is the strong separatrice of the saddle node is contained in the exceptional divisor. And with these definitions, we have a a result of Johann Gensmer that introduces the balance divisor previously, that characterize the second-class foliations as those that the algebraic multiplicity of the foliation equals the algebraic multiplicity of the balance divisor minus 1. We extend the definition of the vector is to a linear combination of invariant curves, not only for a single curve. We introduce this vector u of ones that we'll use in the sequel, and a vector iota that say us when that has a 1 when at the position j when ej is if invariant and 0 otherwise. So this controls there is ones in the invariant components and zeros in the diacritical components. And we define this quantity, Lj, as the algebraic multiplicity at the state j of the foliation, state j minus 1, corrected by adding 1 in the case that the divisor j is dicritical. So this we must to correct by this term. In fact, this is the correct exponent in the equation of the j component that we can factorize in the pullback of one form defining the foliation at the stage j minus 1. So our free result is a formula for the vector L of these discrepancies that we call the vector L of discrepancies in terms of the proximity matrix and the vector associated to a balanced divisor of the foliation. And the idea of the proof is all the results will be like that, is induction on the number of blow-ups, and the case n equal 1 is the base case always, and in this case it follows by this formula, by Gensmer proposition, because L1 is this is that by definition, and the algebraic multiplicity of f equals plus 1 equals the algebraic multiplicity of the balanced divisor, and this minus E1. And this is P, the proximity matrix in the case n equal 1 is just the number 1, so we obtain the result in this case, and after that is induction and use the case n equal 1 at the least in the inductive step. Why we are interested in this type of formulas? Because we wanted to obtain a recursive formula for the Milnor number of a foliation in terms of the combinatorial data of a reduction of singularities. And the Milnor number is defined as the intersection number of the curve P equals 0, Q equals 0, where P and Q are the coefficients of one form defining the foliation. And the result is that we obtain this formula, Milnor number of F in terms of the intersection matrix, the proximity matrix, the identity, the vector U, all entries of which are 1, and the vector SB that controls when the exceptional, the balanced divisor meets each irreducible component of the exceptional divisor. And the idea of the proof is to use the generalized band Essen formula that for one blow-up says just that the Milnor number after blow up is before blow up is the Milnor number after blow up and all the singular points that appear, plus this combination takes into account the discrepancy of the first blow up. If we iterate this formula, we arrive to the sum of all the Milnor numbers after reduction of singularities that are 1. Here is where we use the hypothesis generalized curve, because the Milnor number of side node like that is given by this mu. And the previous result that says that L, the vector L, can be computed in this form. So we put these things together, and we obtain this pairing using the standard scalar product of vectors of n components. We remark that in the case of a curve with reduced equation f equal to 0, we can take the non-critical foliation with first integrand f, and then the Milnor number of the foliation by definition is the Milnor number of the curve. That is defined like this dimension. And in this case, the balanced divisor is just the curve. In this case, we denote SB by SF. So this formula gives also can be applied to the case of a curve. For instance, in the case of the cusp, we have already computed all the ingredients, and the formula holds. So we can check this. As a corollary, we obtain that the intersection number of two curves can be expressed as this pairing using either the intersection matrix A or the proximity matrix P applied to the two sides of the scalar product here with the vector as FSG. Here we use the well-known formula of the Milnor number of a product and the fact that the vectors of a product is sum of vectors. The next index that we revisited is the Milnor number along a separatrice that is defined taking a Puiseux parametrization of the separatrix and a vector field on C0 that push forward by gamma to C2, and given a reduced vector field defined in F, there is a unique vector field in one variable that can be pushed forward to B, and the Milnor number of F along the separatrice C is the vanishing order of this vector field in one variable. It's like the Poincaré index in one variable, a complex variable. And if B is a divisor of separatrices, we define the Milnor number, the F along a linear combination of divisor in this strange way, but that works. And it's equivalent to ask that the function that a curve C, an invariant curve C, associates the Milnor number of F along C minus 1, this function extends linearly. So this formula is equivalent to ask this condition. And the formula for the Milnor number along an invariant curve in terms of the intersection and proximity matrix is given by this expression. As a corollary, if we recall the formula for the Milnor number, not along C, but in general, was the same formula, except that here appear SB. instead of SC. So by automatically, we obtain this corollary, that's the minimum number of a foliation along a balanced divisor equals the minimum number of the foliation. This theorem is a consequence of a well-known formula of the minimum number along a curve is equal to the minimum number of the curve itself and the JSV index that we recall in the next slide. The Gomez-Montsede-Berkowski index is defined of a foliation along an invariant curve C. We take a reduced equation of the curve, and we write a saturated one-form omega defining the foliation in this way, with coprime FGH. And then the JSV index is the vanishing order of the quotient H over G along the curve C is F equal to 0. And can be computed using this integral. This is the remark that we made before, relating the two indexes. And the result for the JSV index is this one, is this expression, simpler expression in terms of the intersection matrix. The idea of the proof is first to reduce to the case that the curve is irreducible, because we know how the JSV index behaves with sums, with the intersection here, and use also that the intersection of the two curves is given combinatorially by this pairing. And then, in the reducible case, we make induction on N in the first stage. After one blow up, we obtain the JSV index by definition of the JSV index as this vanishing order. We obtain that is the JSV index before and after a blow up differ by this quantity. We have L1 is the discrepancy L1 and the algebraic multiplicity of the curve at 0. And iterating this process, we obtain that after n blow-ups, there are two possibilities. If the last point is irregular or singular, if it's singular, the JSV index is 1, and if it is regular, the JSV index is 0. So in any case, is the iota n, this component of the vector iota. And here we obtain the sum of the products of the algebraic multiplicity of the strict transform times this difference, and this can be write like this scalar product. And using the formula for L, we obtain the final expression. As a corollary, we obtain something that wasn't already known, but we have proved it in another form. If B is the union of separatists of a non-critical generalized curve, then the JSV index is 0. The next index we revisited is the Camacho-Sad index, that is with the same expression for the omega when f equal to 0 is an invariant curve. It's this integral that is like a slope of the form with respect to the invariant curve. And it's a slope, it's a complex number, it's no longer an integer. And the Camacho-Sad index of a sum of curves behaves in this way, and we define the Camacho-Sad index of an adapted divisor with weights plus or minus 1 of this form. Then we obtain a result that is not strange that we cannot express the Camacho-Sad index in terms only of the intersection matrix, because this is an integer, and the Camacho-Sad is a complex number in general. So we relate the Camacho-Sad index after the reduction of singularities, and the Camacho-Sad index before reduction of singularities, and the Camacho-Sad index after reduction of singularities, and the difference is controlled by this term.
The minus there is on the screen, right?
The minus?
C equals C0 minus C infinity.
No, it's correct. It's a plus. It's here, no?
No, upstairs.
Here.
Yeah, it's a minus.
Here is a minus. We consider a divisor that, because we want to apply it to a balanced divisor. But in the formula, here is a plus. And the idea of the proof, induction, again, and how Camacho-Sad index behaves after one blow up, that is adding the algebraic multiplicity square of the curve. Finally, we recall the definition of the variation and Bonbot indices that is not, we need to write differently. Well, we need to write the differential of a form defined in foliation like a wedge product of the form itself and a 1-0 form beta, so only differentiable here. If C is an invariant curve, then we define the variation. Well, the variation index is defined of f along C as this integral of beta along C. We have this well-known relation between variation index and GSB index and Camacho-Sad index. And the remark is that this is additive in C. So the formula we obtain is, it's also a complex number. The variation index is also a complex number, so we have the same thing. The difference in between the variation index before the singularization, after the singularization, is given by this integer, and here is linear in C. This is linear in C. And the Bonbot index is defined using the same 1-0 form beta and making the integral along a three sphere around the singular point of beta wedge d beta. If what is well known is if f is non-degenerated, is defined by a vector field whose linear part has non-zero eigenvalues, then the Bonbot is just the trace square over the determinant. Okay. Sorry, the trace square over the determinant. So when we arrive at non-degenerated singularities, the Bonbot index is easy to compute. And the formula for the Bonbot index before reduction is the sum of Bonbot index after reduction that can be computed as trace square over determinant plus this integer. And the idea of the proof is, for any one, is to relate what happens before and after one blow up. And the discrepancy L1 is square is the difference between the two things. As a corollary, after some work, we obtain that if f is a generalized curve with balanced divisor b, then the Camacho-Sad index of f along b equals the variation index of f along b and equals the Bonbon index of the foliation. So when we apply this Camacho-Sad variation index for a balanced divisor, what we obtain is the Bonbon index. This is a generalization of Brunell's results to the dicritical case. He proved for non-dicritical generalized curves, and at that time the balanced divisor was not introduced yet, but he considered the sum of all the separatrices. And the proof of this corollary uses Camacho-Sad index theorem. Well, we summarize the formulas that we have obtained. The algebraic multiplicity of a curve by the proximity matrix, the intersection number of two curves by this pairing with the proximity matrix, the mean number of a curve using that, the discrepancy vector L that plays a role in the proof of the three indexes, the next three indexes, the mean number of the foliation with SB, the mean number of the foliation along a curve C, where the C appear at this level, and the SB index, that's this simpler expression. And the same thing for all these things are integers, and here we have the complex indexes that we have obtained before. And the formulas relating, when we apply all these things to the balanced divisor, we obtain canonical things. We present a non-trivial example to illustrate this kind of computations. It's defined by a one form with a foliation with a meromorphic first integral, f over g. G is a product of three lines. F is a cusp of weights 3, 5. And we made the first blow up. We separate the three lines. We obtain here a 2, 3 cusp, the strict transform of F, and also two singular points at the first divisor. That is the critical. In fact, here the divisor U1 is the critical. But there is two more singular points here that correspond to a double point of two fibers, F plus G, F minus G. When we blow up the point on the cusp, we obtain a second divisor, E2, and here a parabola. And if we made the remaining blow-ups to obtain the desingularization, we obtain this picture. So here we have the fiber F plus G, the fiber F minus G, and a balanced divisor is that. Is F plus G plus F minus G minus G. And one can see that the only the critical component is E1, and the sum of the weights of the separatrices that arrive to E1 is 1 plus 1 plus 1 minus 1 minus 1 minus 1. So the sum is minus 1, and minus 1 is the 2 minus the balance that is 1, 2, 3. 3 points of attaching points or adjacent points. So 2 minus 3 minus 1, and minus 1 is the sum of the weights of this divisor arriving to E1. As before, the proximity matrix at stage 3 is that, and we can complete to the global proximity matrix step by step, and it is looking at the points at the center of the blow-ups. We obtain this matrix, and the intersection matrix that can be computed directly or with the formula from the proximity matrix. And the vectors associated to the separatist f, g, s plus g, f minus g, and the balance divisor. And with all these ingredients, we obtain, we apply the formulas, and we obtain all the invariants that we want. The motivation of this kind of formulas was to understand the bifurcation conjecture by Slopsky that is stated as follows. He defines the minimum number of a pair as the intersection number of these two cards that, in fact, for all purpose, is the minimum number of the pencil foliation defined by the meromorphic function f over g when it has isolated singularity. Then he defines the function that a fiber, that a point P1 that considered as a fiber alpha beta plus beta g equals 0 associates its minimum number. And this function is upper semi-continuous. And so there is generically is the minimum, the minimum number, and for some values, specific values, a finite number of the minimum number grows. And he proposes a formula relating about the total excess of the minimum number. So here is a finite sum, with bifurcation fibers, of the minimum number of the special fiber, the bifurcation fibers, minus the generic minimum number. And he proposed this formula as a conjecture. And he proves its validity when f or g are smooth, and also for the previous non-trivial example that we have considered. And what we do here is to prove this formula using the ingredients that we have introduced. But there is a key lemma that says that for a pencil of we have a canonical some way bifurcation balance divisor like that using the bifurcation fibers. And the idea of the proof of this lemma is apply Riemann-Hurwitz formula to the restriction of the blow-up of the meromorphic function. And then we apply this. Well, this is one way to prove. The formulas we have developed was in fact to have a algebraic manner to manage that. We introduce this linear quadratic function, and so that in fact the minimum number is just the applied to the vector associated to a balance divisor, and then the bifurcation formula is equivalent to this expression, and this expression is equivalent to this sum. In this sum, all these products are the same, and can be factorized, and then we obtain this equality that is always whole. And this provides a new an interpretation of the dimension of the parametric space of the semi-universal deformation of the meromorphic function f over g in terms of the total excess of the middle number. That's all. Thanks for your attention.